This is a partial approach to the calculus one. Did I get this problem for section 3.10, related rates? I think it's broken into 3 to 5 parts on the exam, where they give you the result of the previous part before they ask the next question, or while they ask the next question, so you can earn partial credit. So the first thing that you have to do when you're dealing with a big story problem is read it a couple of times to make sure you understand the givens and you have sort of a broad idea. It's worth the time to do that. Water is filling a pit at a rate of 75 cubic meters per minute. Okay, I got water filling a pit. It's a volume. The pit is an inverted pyramid where the depth P of the pyramid is 3 times the length of the side S of the square. So I'm visualizing a square top and it shrinks down to a point. So it's an inverted pyramid. And I know that there's some kind of relationship between the P and the S and the volume, but I'm not going to worry about that yet. I'm just visualizing it. Find the rate of change of the water when the depth is 15 meters. Oh, okay. So we've got this deep pit and it's filling up. When the bottom is filling up, it's going fast because it's very narrow, and it slows down at how fast it fills up as it gets wider. We're being asked, how fast is that rate of change of the water coming up when the water is 15 meters deep, meaning 15 meters from that point at the bottom of the pit? Oh, the equation for the volume of the water in the pit is V equals 1/3 S squared P. So they gave us that volume formula. So that's great. And oh, find dP dt. Find the rate of change of the water when the depth is 15 meters. Oh yeah, P is the depth, right? P is the depth, and find the rate of change of the water is finding dP dt. Now, we can also figure out some other stuff, right? We're going to want to find dP dt when P is 15. And let's also take a look at other stuff. The water is filling the pit at a rate of 75 meters per minute. So the volume of the water is increasing. Oh, so there's another given. 75 is, now it's a volume, but it's a change in volume. So it's dV dt, right? It's cubic meters per minute, right? Minutes on the bottom, cubic meters on the top. So volume on the top, time on the bottom, 75 cubic meters per minute. Okay, so now we're ready to begin. Well, wait, pit is an inverted pyramid where the depth P of the pyramid, oh wait, the depth P of the pyramid is 3 times the length of the side S. So we also know that P equals 3S. Oh, so it's 3 times as deep as the dimension of the top, right? It's an S by S square at the top. It's a 3S deep, pretty deep pit. Now I've identified all of my givens, right? I can skim through the sentences again. First sentence, I pulled out all the information. The pit is an inverted pyramid. Well, that really connects to the volume formula at the end. The depth P is 3 times the length of the side S. I've recorded that. Find the rate of change of water. I've identified the variable that I need to solve for. And when, so I've identified the instant that we want to find the rate of change of the water. So it'll be a numerical answer. If we're given exactly when the depth is 15, then we'll be able to plug in that value of P and figure it out. But in all related rates problems, we start with the top formula, and we only mess around with variables. No substituting in 15 or 75 now. That's later. 1/3 s squared p. The only thing we're allowed to do here is change of variable, right? The p is 3s, so we are certainly allowed to do that substitution. So we get 1/3. Oh, that's silly. I did my squared backwards. I did s to the s. Let me fix that. Sorry about that slight distraction. 1/3 s squared, and then p is 3s, so I can go back to my algebra. And of course, that simplifies the 3 and the 1/3. Oh, that's s cubed. So we have a very gentle relationship, right? V equals s cubed. Only now, after we've done our job at simplifying the variables, should we think about doing our related rates. So let's do that. Let's take the time derivative of both sides. Well, it's very easy to take the time derivative of a single variable. There's the time derivative of v. And on the other side, it's a nice gentle polynomial. The time derivative of that, as always, it's a polynomial rule, so 3s squared. But just like the chain rule, when you're taking the derivative of s with respect to t, you need that chain term multiplying at the end. So there it is. That's the equation that's going to get me the answer. I'll put a box around it. I don't want to indicate that's the answer, but that's what gets us the answer. How do I know this? Well, take a look, right? We know what P is, so we also know what S is, right? We've been given P as a constant, so we can also use P equals 3S and find out that S is 5. So we know the value of S, that's 5, right? 3 is a constant. We've been given dV/dt is 75, so that's a number. So the only thing left in this equation is ds dt. Now, we were asked for dp dt, but P and S have a linear relationship, so we can solve for ds dt and then convert that using the relationship between P and S, right? P equals 3S, so we can also take the time derivative there. And so dp, right, we also know that dp dt equals 3 ds dt. So once we find ds dt using this boxed equation, we can plug it in to find dp dt. So this is the other necessary equation, which also came from doing related rates to an algebraic relationship. Well, let's go ahead and get the arithmetic done. 75 equals 3 times s was 5, so s squared is 25, and then we have ds dt. Well, 3 times 25 is 75, so this was set up to cancel, divide both sides by 75, you get a 1. So it's set up very nicely. ds dt equals 1. So of course, right, dp dt is 3 times it. And of course, I have ignored the units all along. I could have carried them to sort of confirm that my units were matching my derivatives and so on. But if I do the calculus perfectly and the algebra perfectly, or reasonably, I don't need to worry about units. So only carry the units if you're afraid your calculus or algebra is going to fall apart. It's a change in depth per time. Well, depth is in meters and time is in minutes in this problem. So you could go, I suppose, met per min, meaning meters, shorthand for meters per minute. And that makes sense, right? Linear. P is a linear length. So when the water is 15 meters deep and you're pouring it in at 75 cubic meters per minute, then it's going up at 3 meters per minute. At that moment, it's 15 meters deep. Different answers for different depths. Remember, I spoke of when it's shallower, it's narrower, so the velocity should be faster. It'd be interesting to see how that would come about with the algebra. There it is. That's a related rates problem done very, very carefully. And I want to remind you, the most important thing was the setup, not the work afterwards. That was just algebra. It was the setup at the beginning, identifying when P is 15 is what they said, but then I also pulled in the given, dV/dt is 75. And then I pulled in that sentence that said P equals 3S. And that allowed me to simplify the volume formula that was also given into something that I could do easy calculus on. And then when the easy calculus is done, it turns out they've given you exactly enough information to figure out to know 3 of the 4 variables, so you can solve the 4th.